Measures of relative standing is a fancy way of talking about z-scores and percentiles. So far we've been looking at measures of center, which looks at the entire set of data and what's happening in the middle of it, and then measures of variation, which again looks at the entire set of data and kind of looks at how spread out the pieces of data are from each other and from the average. And now measures of relative standing, we more or less look at individual pieces of data and measure how that piece of data relates to either the mean or all the other pieces of data. So as I said, it's mostly z-scores and percentiles, but we're also going to be talking about quartiles, which is just a special type of percentile, and a box plot, which is just a visual representation of the 5-number summary, which is made up mostly of quartiles and some other things. Okay, so a z-score is a way of describing how far a number is away from the mean in terms of standard deviations. So let's look at a simple example to kind of highlight what it means. Let's say your average was 50, right? And you want to ask yourself, what is the z-score for 60 if your standard deviation was 5? Well, we can see that if our standard deviation is 5, then isn't 60 exactly 2 standard deviations above it? So the z-score would be 2. Okay? So in its simplest sense, a z-score just tells you how many standard deviations above or below a number is from the population, or sorry, from the average, the mean. And here's the formula. So in our previous example, we had x bar was 50, right? Standard deviation was 5. And so if we were trying to find the z-score for 60, we would do 60 minus 50 divided by 5, which would give us 10 over 5, which would give us 2. Here's the interpretation of a z-score. Remember we said before that anything that was in 2 standard deviations of the mean was considered ordinary. And that's this right here. Right? Because a z-score of 2 means you're 2 standard deviations above the mean, and a z-score of negative 2 means you're 2 standard deviations below the mean. So these are ordinary values, and we also saw from our 68, 95, 99.7 rule that this is roughly, right, about 95% of our data. And so the other 5% is split between this area here and this area here. Here's another example. So if the author of the book measured their heart rate at 48 beats per minute, they wanted to figure out if their heart rate was considered unusual, if the average was 67.3 and the standard deviation was 10.3. So we use our simple formula again. 48, right, is our x, minus the 67.3, that's the mean, divided by 10.3. If you want to slap that in your calculator and verify, you'll get an answer of negative 1.87. And since that is within that 2 standard deviation range, it's not considered unusual, right? It has to be bigger than 2 or smaller than negative 2, i.e. it has to be a distance of more than 2 from the mean. Percentiles are a way of describing how much data, right, is below that value. So if you're thinking of your entire set of data and you have one value out of that set. So let's just give an example of scores on a test. And if you've ever taken a standardized test, you've got a percentile rank on that test. But let's say you take a quiz in a statistics class and you have a score of 80 on that test. Well, 80 is your score. You can think of that as that's the x, right? That's the x value that's in this set of data. And let's say there are 40 people in the class. That's your n. And if you put all the scores on the quiz in order and you see where your score is, and it turns out that, let's say, 30 scores, right? 30 basically students scored less than 80. Well, if that's the case, then the percentile for 80, right? 80 is in the 75th percentile because 30 over 40 is 3/4, which is 75%. So 75% of those data values are smaller than 80. And that's all a percentile is. It tells you the percentage of your data set that is smaller than your value. And it's strictly smaller than, right? It won't count the things that are equal to 80. And that's a distinction to make known, because sometimes, rarely, but sometimes some sources compute this number of values less than or equal to x, right? The actual technical definition for percentile is the things that are strictly less than x. So just be aware that if the source that you're reading doesn't state it, you are to assume that it's the percentile means that's the percentage that is strictly less than, but they can compute it as a less than or equal to, but they should tell you. Here's another example. If we're trying to figure out the percentile for 23, 23 being the number of chocolate chips in a particular cookie, then you would put all your data in order, and obviously these numbers represent how many chips were in a random cookie chosen, and it looks like they sampled 40 different cookies and counted up the chips in each one because they had nothing better to do that day. And if we want to know the percentile of 23, then we go and look at where 23 is, and you can see that there are a few 23s, right? So the question is, if you're doing a percentile, what do you count? Well, you only count the things that are smaller than it, which end up being the entire first row, right? These are all smaller than 23. And those are the only things that are smaller than 23. You don't count all of these that are equal to it. And that ends up being 10 out of 40, or 25%. So the percentile for 23 is 25th. 23 chips is in the 25th percentile. Well, since this is a pretty simple mathematical formula, we can also work it backwards. So you could be given a percentile and then try and figure out what number in your data set corresponds to that percentile. So instead of saying, hey, what's the percentile for 23 chips, you could say, how many chips do I have to be in the 50th percentile or 70th percentile? And that's what this formula does. So things that we've already seen, right? N still means number of things in your sample, right? In this case, K is new to us, and that's just the percentile that we're looking for. L is our answer. They call it the locator. That just tells us where in the list of data values we are. And then P to the kth ends up being, the kth percentile. So if we're looking for the 50th percentile, then that just means K equals 50 in this formula, right? Now, actually using this formula is pretty easy as far as the math is concerned, but once you get your answer, it's a little tricky because you have to pay attention to this flow chart. So the first thing you do is you sort your data, obviously from smallest to biggest, because again, if we're trying to find where something is in the data, it doesn't make sense unless we put that data in order. Then we compute this number. So let's look at an example real quick. If let's say our set of data, we have 300 pieces of data, and we're trying to find, let's say, the 40th, right? We're looking for the 40th percentile. So that means K equals 40. So according to this formula, our locator is going to be 40 over 100 times 300, and we get 120. So that means we now move to this step because we have our answer, and it asks, is L a whole number? Well, yeah, we got a whole number. We got a perfect number of 120. So if it is, we go this way, yes, and it says the value of the kth percentile, the 40th percentile that we're looking for, is midway between the Lth value and the next value. So since we got 120, according to this, we go halfway in between that and the next number. So we would go to our list of numbers and we would count up and we would find, okay, this x is the 120th one, and then this x is the 121st one, and then we would take the average right in between. We'd go halfway in between them, and that would be the number that we would report as the 40th percentile. Because let's say this number was a 17, and this number was 18. Then if we say 17.5, then in fact all 120 of these things are less than that. So that's the cutoff, right? That's where our 40th percentile is. Now a similar example, let's say we did all of our work with this formula, and instead we got an answer of 120.2. Well, then when we get to this step, is L a whole number? You go, no, it's not. It's got a decimal. So now you change L by rounding it up. See, in this, you got to pay attention to this. You round up. So even though this is a decimal smaller than 5, you would still round up to 121, and then 121 would be the one that you were looking for. So again, we go back to our list, and here's the 120th, and then here's the 121st, and this 18 ends up being our answer. Okay, so that's how to work it. If you get a whole number, you go halfway in between that and the next one in the list. And remember, the 120 represents the number of things, right? It doesn't represent the value of the data. It represents you count down and you go, okay, that's the 120th number in the list. If the number is not a whole number, you round up regardless of what its decimal is, and then that's the number you choose as the kth percentile. Okay, quartiles, as I said, are just specialized percentiles. So the first quartile is just the 25th percentile, and then the second is the 50th percentile, which is also what we call the median, and then the third is just the 75th percentile. So if you look at this next picture, it kind of helps visualize it for you. If you have all of your data, right, this number line represents the entire string of data that you have, all of your pieces of data lined up in order from smallest to biggest. Well, if you take that data and cut it into fourths, right, these represent fourths, then Q1 is just the cutoff for the first quartile, the first quarter of data, right? So there's 25% of your data below it, and then Q2 has 50% below it, and then Q3 has all 75% below it. That's all the quartiles are. We gave them a special name because we use them a lot. Okay, there are some other things on this slide that we don't really use a lot. The only thing you want to pay attention to is the IQR, the interquartile range. And that's the difference between Q3 and Q1. So back on this slide, we can see that the interquartile range is just this distance right here. And by distance, we mean how far apart are the two numbers that end up representing Q1 and Q3. I mean, we know it's 50% of our data, but what's the actual distance, right? If Q1, let's say equals 12, and Q3 equals 25, then this distance ends up being 13. That's what IQR is. The 5-number summary is a very typical thing used in statistics. It just describes your data very quickly. You give the reader the minimum value, the first quartile, the second quartile, which is the same as the median, the third quartile, and the maximum value. So the reader can get an idea of the overall spread of your data by looking at these numbers. A box plot is just a visual representation of those 5 numbers. So to construct a box plot, all you got to do is find your 5-number summary and then draw a box that represents those numbers, and you just have to pay attention to keeping everything to scale. The idea is you want to visualize the box actually sitting on top of the number line. So if something is supposed to be between, like our example, 13 and or 12 and 25, I think it was, then it would sit above 12 and 25 on the number line. So here's a picture. You'll notice that this scale is not that great, and obviously we can't be super perfect by hand, but if you make it with technology, it's perfect. This distance here should represent, right, if this is 4.5 and this is 35, it should represent a distance of basically 30. And then this distance here, since we're going from 35 to 68, should be basically a distance of 33. And if you look at those two, that one is longer than that one. So they didn't do a great job of their scale, right? These two distances should be about the same, but this one should be a little bit longer. And then going from 68 to 113, so that's 70, so that's 45. Well, it's definitely longer than that, so that's pretty good. And then from there to there is 112, which should be, like almost 2.5 times that size. So that's pretty good. So their scale's not too bad, but you get the idea. The scale should reflect the numbers. And by looking at this box plot, you can see that the majority of the data, right? Because this box represents Q1 through Q3. That's 50% of your data. You can see how the middle of the data, right, that middle 50% is actually off center. You've got a longer tail over here than you do on that side. So you don't have a symmetrical distribution of your data. You don't have that nice bell curve that we saw in the other video, right? We don't have something that looks kind of symmetrical. This one looks a little bit more symmetrical, so it's got more of that normal distribution that we're looking for. This one is severely skewed, right? You've got that huge tail off to the right. So if you remember what it means to be skewed, which way is this? Is it skewed left or skewed right? And hopefully you're all screaming at me. It is skewed to the right. Right, it's always skewed in the direction of the tail, and that has a big tail, right? If we drew a curve over this thing, it would look something like this, and then a big old tail on that side, skewed to the right. Okay, outliers and how they create a modified box plot. An outlier is just a value that lies way out there, right? It's way far away from the majority of the data. So if we look at this, this is an outlier out here because look at how far away it is from the middle part of the data. I should say the big chunk, right, where a lot of the data is. So that would be an outlier most likely. An outlier has huge effects, as we've said before, on the mean and the standard deviation, and it can also screw up your histogram if you're trying to describe your data visually, because now all of a sudden you have to have a bin that's way out where the outlier is, and so your scale gets all messed up. If you're going to create a modified box plot, you're going to create a box plot that actually shows when things are outliers. And in order to do that, everything is still the same. You still do your 5-number summary, and you still calculate all those things. But the next step is you calculate that IQR that we were talking about, right? Which is Q3 minus Q1. Remember, IQ, your inner quartile range, just equals Q3 minus Q1. It's just the distance between your two quartiles. And then you take that and you multiply it by 1.5. So that's the next step. Then you start drawing your box plot as usual. So you would come down here and you would start with the box in the middle. Right? This is Q1. This is Q3. This is your median, Q2. You calculate this distance, right? This is your IQR. And the idea is you take that, you multiply it by 1.5, and then you figure out what that number is. let's say the top of your, let's say Q3 is 70, and let's say Q1 was, we'll make it easy, 60. So IQR equals 10, 1.5 times it equals 15. The idea is you now go up 15 from 70, and you have a cutoff of 85. Go down that distance from 60, and you have a cutoff of 45. And now if you have any data in your set that are smaller than 45 or greater than 85, you represent them with asterisks. And then when you create those whiskers, instead of going to the minimum and maximum like you do on your 5-number summary, you stop at whatever value you have that still isn't an outlier, right? And then you would label these, and like maybe this is 88, 90, 92, maybe this is 38, and that would be a modified box plot. If you had 85 in your data, right, if 85 was actually a data value, then this whisker would actually stop right there at 85. So the tie goes to the runner, right? If you have a number that lands right on one of these borders, it's okay. It has to be actually farther out, right? It has to be either bigger or smaller. So this is just discussing what we've talked about, where you use a little asterisk or something for the outlier pieces of your modified box plot. Here's an example of one that was done in technology, where the symbol they used obviously was just a dot. And so that's it. That's everything about measures of center, measures of variation, and measures of relative standing. So far we've looked at all of these things with how to sample and how, the context of data and how to describe it, and now kind of the descriptive statistics, and soon we'll be moving on to inferentials.